In this section, we're going to take a look at an introduction to the concepts of sequences and series.
In common language, a sequence is just an ordered list. For example, if I write down 1, 2, 3, 4, 5, that's a sequence. And if I write down 5, 4, 3, 2, 1, that's a different sequence. Because even though it contains all of the same numbers, they're in a different order. So in common language, a sequence is an ordered list of numbers or variables or whatever you're dealing with. However, we're going to have a more formal definition here, which will make some of our things a little easier to handle. We can think of a sequence as a function. So the common thought of a sequence is it's an ordered list. There's a difference between these two because there's an order difference. But the more formal definition is as follows. Definition: an infinite sequence. Infinite. There are going to be two kinds of sequences. These are called finite because they have a beginning and an end. However, there are also infinite sequences which have a beginning but no end. Right? So, for example, here, this I'll say this one is a finite sequence because it begins and ends. Right? There's 5 terms. But if this sequence kept on going forever and ever and ever, then this would be an infinite sequence. So we're going to start by defining an infinite sequence. A finite sequence is basically just some terms out of an infinite sequence. So here you go. An infinite sequence, which is denoted with the symbol a sub n, surrounded by braces, the same way you would surround a set with braces. This is a function. From the set of counting numbers, the counting numbers being the ones that you count with, 1, 2, 3, 4, 5, and so forth. From the set of counting numbers, and for us, they're always going to be real numbers. Hypothetically, you can have an infinite sequence made up of complex numbers. Right? You can have made up of any kind of number you like, but we're going to stick with real numbers. So from the set of counting numbers to the real numbers. The function will have values that are called the terms of the sequence. The function values are the terms of the sequence. And are represented by a sub 1, comma a sub 2, comma a sub 3, comma dot dot dot, comma a sub n, comma dot dot dot. If the sequence consists of only the first n terms, in other words, it doesn't keep going after this point, it just stops, any sequence that consists of the first n terms is called a finite sequence. All right, so let's start off with an example. The reason I mentioned that although you can think of a sequence as an ordered list, that things will be made a little simpler if we think of it as a function is because, well, if we have a function, we can often write a rule for the terms of that function. So let's say, for example, I have the sequence a sub n, and here it doesn't always have to be an a. You can say b sub n or c sub n, and in fact, we often do write them using different letters to distinguish between the two of them. So this would be the set made up of a sub n's, this would be the set made up of b sub n's and c sub n's. If you have to deal with more than one sequence in the same problem at the same time, we often do give them a different letter. Okay? All right, so here is a set of terms of this function. Okay, but what are the terms of the function? Well, we can define them explicitly. We can say something like 5x minus 2. Or we can say something like negative 1 to the power of n over 2n minus 1. Like that. And here we have defined an infinite number of terms. Oops, sorry, that should not be an x, that should be an n. So in fact, that is one big difference between the notation of a regular function and the function that we would use to define a sequence. Here we use n as our variable. It's a minor difference, but it's meant to signify the fact that we're not dealing with a continuous case. Here, n, the number that we plug in, should not be 1/2 or 2/3 or 7.3. It should only be made up of counting numbers. That's why we say it's a function from the set of counting numbers to the real numbers. In other words, the counting numbers are the domain of your function. So here your n should never be 1/2 or -6 or 7.3. It should always be a counting number. 1, 2, 3, 4, 5, 6, 7, and so forth. But notice there's no limitation on what counting number it can be. So we can keep going on forever. The way we can write this out using the roster method, the roster method meaning we simply start listing terms instead of having a rule for it, we can simply start plugging in counting numbers and seeing what we get as a result. So here we have the set that's made up of, all right, well, let's start with the smallest counting number. That's the number 1. If I plug in 1 right here, 5 times 1 is 5, minus 2, that's going to give me 3. Now if I plug in the number 2, which is the next counting number, 5 times 2 is 10, minus 2 will be 8. If I plug in 3, 5 times 3 is 15, minus 2 is 13. If I plug in 4, 5 times 4 is 20, minus 2 is 18. If I plug in 5, I get 23, and so forth and so on. Look at this. So you can write a sequence using either the rule for what its terms are, or you can actually just list the terms. Now, since the infinite series has an infinite number of terms, you'll never actually be able to write them all. So if you have a rule to tell you the nth term, that's actually a more convenient way to write it. But if you don't have a rule, sometimes you'll have a sequence without knowing exactly what rule, what function gets you these numbers, then you may have to write it out this way and then just say ... That's the best you can do to write it out. Note that this right here is your a sub 1 because it's the term in the set of a's that you got by plugging in the number 1. This is a sub 2 because it's the term that you got in your sequence of a's that you got by plugging in the number 2. And this is a sub 3 and a sub 4 and a sub 5 and so forth. So that's what we mean by those subscripts. The subscripts are telling you two things. One, it's telling you what number did you plug into your rule to get you that term. And 2, it's telling you the position in line. Yeah, that's the first number in line, the second number, the third number, the fourth number, the fifth number, and so forth and so on. Whenever you don't know what term you're dealing with, you just call it a sub n. Either you don't know what term you're dealing with or you haven't decided which one you want to deal with yet. Instead of writing out, oh, I want the 5th term, the 4th term, the 9th term, since you don't know which one it is yet, you simply write the nth term. And in fact, that's what this one's called. This one's called the nth term. We can write this one out the long way as well by simply plugging in some numbers and seeing what we get. If we plug in, again, the smallest counting number is 1. So let's plug in 1. Negative 1 to the first power is negative 1 over 2 to the first power is 2 minus 1 is 1. Okay, so that's what I get when I plug in the number 1. If I plug in number 2, negative 1 squared, that's a positive 1, over 2 squared is 4 minus 1 is 3. And then if I plug in 3, negative 1 to the third is negative 1. 2 to the third is 8 minus 1 is 7. 4, negative 1 to the fourth is positive 1 over 2 to the fourth is 16. 16 minus 1 goes 15. If you plug in 5, negative 1 to the fifth power is negative 1. 2 to the fifth is 32. 32 minus 1 is 31, and so forth and so on. This is called the roster method of writing out a sequence. You literally just start listing terms. So this right here is called the roster method, where you literally just start listing terms. All right, so go ahead and give this a try. Here is a sequence given by its nth term. So here I'll call this one C sub n, and it's going to be given by the rule where the nth term is 3n minus 5. And then here's another one, d sub n, the sequence of d's, where the nth term of that sequence is given by the rule negative 1 to the power n over, let's say, 3 to the n plus 1. Okay. Go ahead and use the roster method to write out the first 4 terms. Why 4? Just because you have to stop eventually, right? So you can go as far as you want. You can write 10 terms, 50 terms. But if you can write out the first 4 terms, you're pretty confident that you understand how this notation works. So go ahead and do that. Pause the video, give yourself the time you need, and write out the first 4 terms of each of these sequences in the roster form. And once you're done, go ahead and unpause and we'll go through it together. Okay, so if we have the first term, you're plugging in the number 1. The second term, you plug in the number 2, the number 3, and then finally the number 4. All right, so 3 times 1 is 3, minus 5 is negative 2. Notice that your results can be positive or negative. Your results can be fractions, but the number you plug in must be a counting number. So that's your a sub 1. Your a sub 2 is what happens when you plug in the number 2. 3 times 2 is 6, minus 5 is 1. If I plug in 3 here, 3 times 3 is 9, minus 5 will give us 4. If you plug in 4, 3 times 4 is 12. 12 minus 5 will give us 7. And then, of course, this does keep on going. We only wanted to write the first 4 terms to give ourselves a feel of what it looked like, but that does keep on going forever. Same thing for this one. You can find the terms by simply plugging in sequential values of counting numbers. So negative 1 to the first is negative 1 over 3 to the first is 3, plus 1 is 4. If you plug in n is equal to 2, negative 1 to the second power, that's positive 1. 3 to the second is 9, plus 1 more is 10. Okay. If we plug in the number 3 to get the third term, negative 1 to the third is negative 1 over 3 to the third is 27, plus 1 more is 28. Fourth term, we plug in the number 4 for n. Negative 1 to the power 4 is positive 1 over 3 to the power 4 is 81, plus 1 more will give us 82. And this does keep on going forever. So we'll put our ellipses here to signify the fact that this does keep on going forever. Note that these are all infinite sequences. They keep on going forever. However, if you took only the first 2 terms, the first 3 terms, the first 20 terms, you would have a finite sequence. So any sequence that consists of the first n terms, and again, n doesn't matter what it is as long as it's some number. So if it consists of the first 5 terms, the first 50 terms, the first 2 million terms, whatever, as long as you can get to the end of it, it's considered a finite sequence. Even if it's super long, even if it's trillions of numbers long, that's fine. As long as you can eventually get to the end, it's still considered a finite sequence. Infinite sequences have no end. They keep on going ad nauseum, forever. Now, I mentioned a moment ago that there is a difference between a function that you're used to and the function that gives us an infinite sequence, or even a finite sequence. And that is that the domain of the function that gives you either an infinite or a finite sequence is going to be the list of counting numbers. counting numbers. This is made more clear if we look at the graphs of some of these functions. So for example, let me go ahead and graph two different functions. The first one I'm going to graph is going to be, I'm going to graph f of x equals x squared minus 1. Okay? And then the other one I'm going to graph is I'm going to graph a sub n equals n squared plus n squared minus 1. So right now these may look very similar. And in fact, of course, they look very similar. They look exactly the same except for a different variable. That's x squared minus 1. That's n squared minus 1. However, by having an x here, the idea is that this is a continuous function, the kind that you've been used to since algebra. But by having an n here, that's supposed to signify the fact that you no longer have a continuous function. Your domain is made up of only counting numbers. This is made clear when we look at the graphs. Okay. All right. This one is the parabola that you've been used to forever, right? X squared, that's the parabola starting from the origin, going up to the left and up to the right. Oh, well, x squared minus 1. Okay, you take the standard parabola and make it come down by one step. So instead of starting at the origin, you start down here at 0, negative 1. And this comes up this way and up this way. Okay, so that is the standard parabola that you've been used to since algebra. Shifted down slightly. Over here, you don't have that entire curve. You're only plugging in counting numbers. So here you can't plug in 0. You can't get this point down here. You cannot get 0, negative 1, because in order to do that, you would have plugged in 0. And you can't have that. You can plug in 1, 2, 3, 4, 5, 6. You can only plug in counting numbers. So if I plug in 1, well, let's see. If n is equal to 1, then a sub n is 1 squared, which is 1, minus 1, which is 0. If I plug in 2, 2 squared is 4, minus 1. Okay, that's 3. If I plug in 3, 3 squared is 9, minus 1, that's 8. If I plug in 4, 4 squared is 16, 16 minus 1 is 15, and so forth and so on. So when I plot those, I have 1, 0. I have 2, 3. I have 3, 8. And I have 1, 2, 3, 4, 15 up there. I'm not connecting my dots because there's nothing in between my dots. My points are only these. I don't have anything negative here. I don't have anything between the points. Notice here, yeah, I can plot points, but then I connect the dots because everything in between my point is also valid. Yeah, I can plug in 0 and 1 and 2 and 3, but also, I could also plug in 1.6 and 1.1 and 1 and 1/8 and everything else in between. So here, this is the big difference. Here, it's continuous. It goes on in both directions and it includes everything in between the points. Here, it's only the points. You may or may not be familiar with these phrases. You're definitely familiar with this phrase. This is a phrase from algebra. This is a continuous graph. On the other hand, if you have this one, this is called a discrete graph. Discrete. It will sometimes help us to visualize what graphs look like. And in the case of a sequence, remember, what you're visualizing is never connected. It's an individual set of, it's a set of individual points, discrete points, separated from one another. Okay? Now, we began by stating that a function can define a sequence. Now, sometimes those functions are not necessarily easy to come by. In fact, sometimes they're not even desirable, because some sequences are best defined not by saying, okay, I know what my first term is, I know what my second, my third, my fourth, my fifth, and so on, but rather it's more convenient to say, I can find the next term as long as I know the previous one. I can find the second term as long as I know the first one. I can find the third one as long as I know the second one. In fact, here, that is the case. If you know what one of your terms is, you can find the next one by adding 5. So as long as I know what the first one is, oh, I can add 5 to get the next one. Oh, well, once I know what that one is, I can add 5 to get the next one, and so forth, and so on, and on, and on, and on. Not everyone's like that. Not every sequence will allow you to easily find the next term from the previous one. But in some cases, you can. In those cases where you can define the next term based off of the previous one, you have what's called a recursion formula. So, definition. A sequence can be defined by a recursion formula which defines the nth term as a function of the n minus first term. So here you could fill in the blanks. The recursion formula will tell you the 20th term based off the 20 minus 1. Okay, 19th term. You want the 50th term? Okay, well, what's 50 minus 1? 49. Okay, so you'll define the 50th term using the 49th term. What a recursion formula does is it tells you, okay, you know what one term is, this will tell you the next one. Whenever you have a recursion formula, you are given not only the recursion formula, but also a term to get you started. You need, at the very least, the first term of the sequence, and from there, the recursion formula will define all the rest of them. So, for example here, let's write the first 4 terms of the sequence that's defined as follows. We're going to be given 2 pieces of information. We're going to be told our a sub 1, the first term. So here it's asking you to write the first 4 terms. They already give you the first one. Okay, so a sub 1 is equal to 3. And then you're given the recursion formula. You're told that a sub n is equal to 5 times a sub n minus 1 plus 1. This n minus 1 is not telling you to do anything. It's not telling you to subtract 1 from your number. It's not telling you to subtract 1 from the number 5. These are not directions to do anything. They're a label. So a sub n minus 1 is, okay, you want the nth term, you're going to use the n minus first term. So for example, I already know a sub 1. So let me use my formula to find a sub 2. A sub 2 will equal to 5 times a sub n minus 1. Well, right here I said n is equal to 2. So here 2 minus 1 is 1. Oh, so it's going to be 5 times a sub 1 plus 1, which we know what to do with that. We know a sub 1 is 3, so that's going to be 5 times 3 plus 1. That's 16. Oh, but now to find a sub 3, we already have the first one and the second one. We're going to take 5 times, well, if we're looking for a sub 3, we're going to use a sub 3 minus 1. We're going to use a sub 2. So that's going to be 5 times a sub 2 plus 1. But a sub 2 is the one we just found. So plug that in. That's 5 times 16 plus 1. Okay, well, 5 times 16 is 80, plus 1 is 81. And now we're going to find a sub 4. All right, the question is to find the first 4 terms. So the fourth term is now going to be 5 times, notice, to find a sub 2, you use a sub 1. To find a sub 3, you use a sub 2. You use the one right before. That's what we mean by a recursion formula. It recurs. It happens over and over again. It repeats in a cycle. A sub 4 is equal to 5 times a sub 3 plus 1. Okay, so it's going to be 5 times the previous answer, which is 81, plus 1. All right, well, 5 times 81, that's 405, plus 1 more, that's 406. And if you wanted to find the next one, the 406 would be the basis of the next one, and on and on and on. You would use this over and over again. The process would recur. It would happen over and over again. Hence, recursion formula. So, go ahead and give this a try. Go ahead and write, same as before, write the first 4 terms of the sequence, and this one will, just like the previous one, be defined with a recursion formula. You're told the first term of your sequence will equal to 4, and then you're told to find the nth term. You're going to take double the n minus first term, and then you're going to add 3. Okay, so go ahead and give that a try. Pause the video, give yourself the time you need, and write the first 4 terms of the sequence. Once you're done, go ahead and unpause the video, and we'll go through those together. All right, so we already know your first term. Let's find the next one. A sub 2. Well, that's going to be double a sub 1. You're going to use the one right before, one step earlier. So 2 times your a sub 1, 2 times 4, plus your 3. 2 times 4 is 8, plus 3 is 11. So there you go. There's our second term. But now we'll use that second term to find our third term. A sub 3 will be double the second term, the one right before that. Okay, that was 11, plus 3. 2 times 11 is 22, plus 3 more is 25. And now to find our fourth term, we're going to use the third one. You always use the answer of 1 to find the next one. So it's going to be 2 times the third term, which we now know is 25, plus 3. 2 times 25 is 50, plus 3 is 53. And those are our results. Our first 4 terms are going to be 4, 11, 25, and 53. Okay, now, whenever we define a sequence, we will sometimes do it with a formula, define it as a function of n. Other times we'll use a recursion formula, define the nth term as a function of the n minus first term. But in any event, we're going to need some rule that gives us the terms of our sequence. Oftentimes the rules that give us the terms of our sequence are just based in basic notation. You're going to add, you're going to subtract, you're going to multiply, you're going to divide, you're going to use powers. However, there is another operation which is used a lot in many sequences, which you may not be familiar with, and that's what we want to talk about now. Let's talk about factorial notation. All right. Factorial notation will look like this. This is read as 5 factorial. It doesn't mean I'm very excited about the number 5. This is read as 5 factorial. Okay, so what is that thing? All right, to compute a factorial of a counting number, what you're going to do is you're going to take the number itself and start counting down from 5 until you get down to 1. Okay, so 5, 4, 3, 2, 1. And once you have all those written out, you're going to multiply them together. So 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. And 120 times 1 is still 120. So 5 factorial is 120. That's called factorial notation. For factorial, you would start from the number 4 and count down. 4 times 3 times 2 times 1. So 4 times 3 is 12. 12 times 2 is 24. Times 1, that's still 24. 3 factorial, that's 3 times 2 times 1. That's 6. 2 factorial, that's just 2 times 1, which is 2. And then 1 factorial is just the number 1. Notice how quickly that grows. 1 factorial is 1. 2 factorial is 2. 3 factorial is 6. 4 factorial is 24. 5 factorial is 125. Take a moment and find 6 factorial. Pause the video if you need to, and once you're done, go ahead and come back and we'll go through it together. So 6 factorial is you start from the number 6 and count your way down. 6 times 5 times 4 times 3 times 2 times 1. 1 times 2 is 2. Times 3 is 6. 6 times 4 is 24. 24 times 5 is 120. If you take 120 and multiply by 6, you get 720. Notice that factorials grow very, very quickly. 1, 2, 6, 24, 120, 720. And they just keep getting bigger from there. We define factorials only for counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We don't define 3½ factorial. We don't define 2/3 factorial. We do, however, for convenience, define 0 factorial. You say, what is 0 factorial going to be? Is it going to be 0? You would think so. That would make sense, I guess. But 0 factorial is equal to 1. You say, how is that 1? Well, let's see here. First of all, notice the pattern that to get from 1 factorial to the next, you're multiplying by the new number in front of the factorial. In other words, from 1 factorial to 2 factorial, we're multiplying by 2. From 2 factorial to 3 factorial, you multiply by 3. 2 times 3 is 6. From 3 factorial to 4 factorial, you multiply by 4. 6 times 4 is 24. To get to 5 factorial, you multiply by 5. And to get to 6 factorial, you multiply by 6. Okay, well, if going up means I'm multiplying, going down means I'm dividing. So to go from 6 factorial down to 5 factorial, I need to divide by 6. To go from 5 factorial down to 4 factorial, I need to divide by 5. And that's true. 120 divided by 5 is 24. If I want to go from 4 factorial to 3 factorial, I need to divide away by 4. 24 divided by 4 is 6. To go from 3 factorial to 2 factorial, I'll divide away the 3. 6 divided by 3 is 2. And to go from 3 factorial down to 2 factorial, I need to divide by the 2, which 6 divided by 2 is 2. To go from 2 factorial down to 1 factorial, I need to divide by my 2. Okay, well, that's fine. 2 divided by 2 is 1. Oh, but if I want to take one more step down, well, then I would divide by 1. And 1 divided by 1 is still 1. So we define 0 factorial as being 1. If you divide by 6, that's the next one. Divide by 5, divide by 4, divide by 3, divide by 2, divide by 1. Oh, but 1 divided by 1 is still going to stay 1. So we're going to define 0 factorial as being 1. And then you say, well, can't I go further down than that? Couldn't I divide by the next number to get like -1 factorial? No, the problem with that is the next number you're dividing by is 0. And, well, dividing by 0 is undefined, right? All right, you divided by 6, 5, 4, 3, 2, 1. Ooh, now you're going to try to divide by 0? No, you can't do that. So here we have to stop. That's the lowest number we can get to. So here, one thing to note, and this will come in handy in many instances, 0 factorial is equal to 1, sort of by definition. Really, the factorials are defined from 1 going up, but as long as we keep track of that pattern, we can justify saying, oh yeah, let's also go ahead and have 0 factorial equal to something. For reasons that are not entirely clear now, but which will become more clear in calculus, some of your sequences will involve factorials. In fact, many of them will involve several factorials. This phrase will not make sense to you right now, but it has to do with repeated differentiation. If that doesn't make any sense, that's fine. By the time you get through the end of Cal 1, that will make sense, and you'll know why your factorials keep appearing over and over again. But for now, we're simply going to state how we can simplify expressions using factorials. If factorials appear in a lot of your sequences, well, then we kind of want to know how to do arithmetic with factorials so that we can simplify stuff and evaluate stuff. All right? So let's simplify some expressions that involve factorials. So let's take a look at some examples. We're going to simplify the following things. Simplify. All right. Let's say we have 20 factorial divided by 2 factorial times 18 factorial. Okay. That is going to be really big. Now, if you start by taking 20 factorial, that's going to be kind of a difficult thing to work with. Right? Because here, if I pull out a calculator, remember factorials grow very quickly. 20 factorial is that number, 2.4 times 10 to the 18th power. Or in other words, move your decimal 18 spaces over. Let's say I have a slightly bigger number. Instead of 20 factorial, let's say I do 30 factorial. Then I have to move my decimal over 32 spaces. And if I have something sufficiently big, then I have to move 64 decimal spaces over. In fact, I believe my calculator can handle up to 70 factorial. So let's see, what does 80 factorial do? Yeah, the calculator just says, yeah, I can't do that. I'm sorry, that's too big. So factorials grow extremely quickly, so computing them manually or even with a calculator can be challenging, which is why we instead consider what factorials are saying. Notice that 20 factorial is 20 times 19 times 18 times 17 times 16 times ... 3 times 2 times 1. Here I pretty much get tired and I don't want to write them all. So here, just assume I wrote them all. 20, 19, 18, 17, 16, 15, 14, all the way down to 1. Now you say, well, yeah, that's really big, so I don't want to multiply that all out. Well, you don't have to. Because look, 2 factorial is 2 times 1. Okay? 18 factorial is 18 times 17 times 16 times ... times 3 times 2 times 1. You started from 18 and counted down. But notice that most of these numbers now cancel out. 1 divides 1, 2 divides 2, 3 divides 3, 4 divides 4, all the way out. 16 divides 16, 17 divides 17, and 18 divides 18. So notice that even though both of these numbers are very, very big, they cancel each other out almost entirely. So really, all you're left with is 20 times 19 over 2 times 1. Well, I know 2 times 1 is 2. Oh, and look, the 20 goes into, the 2 goes into 20 10 times. So here, I can say 20 times 19 over 2, or I can just reduce these to be 10 times 19, which is 190. And there we go. 20 factorial over 2 factorial times 18 factorial, that's 190. Not 190 factorial, just 190. Now you might say, well, that's not really important. I mean, you just pulled out a calculator. Couldn't you have done that with a calculator? The answer is, I believe so. Now, again, if my numbers are sufficiently big, like 80 factorial, then no, my calculator can't handle that. But for smaller, relatively small numbers like 20 factorial, I can then divide that by 18 factorial, and then divide that by 2 factorial. And as long as I know how to use my calculator, yeah, I get 190. No problem. Well, no problem assuming you have constants. What happens when you have to simplify an expression that involves variables with factorials? For example, let's say I have n minus 1 factorial over n plus 1 factorial. Well, now there's nothing to plug in. I don't know what my numbers are. So now you might say, well, okay, just go ahead and choose n is equal to 5 and plug that in. Okay, but n is not equal to 5. Sure, you can find what you get if n is equal to 5, but that's not the question. Here, you're asked to find this expression as it is, not with any specific value. And in fact, there's a reason for that. You'll see again in calculus. You won't care what the numbers are. You're going to want to simplify the expression because the expression itself tells you something. There's not going to be any number that tells you anything. It's the expression itself. So here we would want to simplify this, and unfortunately, in a situation like that, no calculator is going to be able to help us. But we can do the same thing here. N plus 1 factorial. That means n minus 1 times, okay, whenever you have a factorial, you start with that number and then keep subtracting 1 each time. Okay, well, that's already n minus 1. If I subtract another one, that's n minus 2. If I subtract another one, that's n minus 3. If I subtract another one, that's n minus 4. And that will keep going. And the nice thing is that factorials always keep going, and even though they have a different beginning, they always have the exact same end. Eventually, you're going to get down to 3, and then 2, and then 1. Always. Every factorial ends the same way. They all begin with different numbers, but at the end, you're going to go down to 3, 2, and eventually 1. Okay, so that's written out the long way, n minus 1 factorial. Okay, what about n plus 1 factorial? Well, that's going to be n plus 1. And now we're going to start subtracting 1 at a time. So if you take n plus 1 and you subtract 1, well, that leaves you just your n. Okay, now subtract 1 again. Well, that's n minus 1. Subtract 1 again. Well, that's n minus 2. Again. Well, that's n minus 3. Again, that's n minus 4. And you'll keep going and going and going until eventually you get down to 3 and 2 and 1. And notice that now, even though these are not constants, they're still dividing into each other. Just like above, anytime you have a number divided into itself, it's equal to 1. So here that's 1. 2 over 2 is 1. 3 over 3 is 1. 4 over 4, 5 over 5, 6 over 6. But over here, n minus 4 over n minus 4, that's also 1. And n minus 3 over n minus 3. And n minus 2 over n minus 2. And n minus 1 over n minus 1. All of these divide away to give you the number 1. So in the end, your expression is 1 times 1 times 1 times 1 times 1 times 1 times 1, which is 1, over all of these are 1 times 1 times 1 times 1 times n plus 1. Those can be multiplied. N times n is n squared. 1 times n is n. And that is your result. N minus 1 factorial over n plus 1 factorial is 1 over n squared plus n. We don't know what n is, nor does it really matter to us right now. We can still simplify factorials. So go ahead and give this a try. Take a few moments and simplify the following. I'm going to give you one that involves numbers. So can you grab a calculator? Sure, but I would suggest against it so that you practice how this works because, well, with variables, calculators are not really an option. So go ahead and simplify. The first one will be, oh, I don't know. Let's do 30 factorial over 3 factorial times 27 factorial, like that. Go ahead and simplify that. Incidentally, this actually is a meaningful thing. I didn't just pick numbers at random. This does mean something which we'll talk about later when we talk about combinations. But for now, simplify this, and then also go ahead and try this one. You're going to simplify, let's go with 2n plus 1 factorial over 2n plus 3 factorial. All right, pause the video, give yourself what time you need, and once you are ready, go ahead and unpause and we'll go through these together. All right, so these can be simplified by expanding them out. 30 factorial is 30 times 29 times 28 times 27 times 26 times ... until you get down to 3, and then 2, and then 1. 3 factorial is 3 times 2 times 1. And you might be tempted to cancel those with these, but you're better off using the much bigger number. So here that's going to be 27 times 26 times 25 times 24, down to 3, 2, and 1. And notice that here, starting from 27 all the way down to 1, that's the same as this 27 all the way down to 1. So these will completely divide away. So now you're just left with 30 times 29 times 28 over 3 times 2 times 1. Here we can simplify that just a little bit more. Notice that 30 goes into 3, that's 10. Let's see anything else. Here 28 goes into 2. 28 divided by 2 is 14. And that's it. You're dividing by 1, so really it's just the numerator on top. So here we go. We're now going to just multiply those three numbers together. We're going to take 10 times 29, so that's 290. And then when you multiply 290 by 14, that'll be what? 4060. And there's our result. So if you take 30 factorial over 3 factorial times 27 factorial in the denominator, you get 4060. This one, you're going to multiply starting from 2n plus 1, and then you're going to start subtracting 1 at a time. So 2n plus 1, if you subtract 1, that's just 2n, because the 1's gone away. If you subtract 1 more, that's 2n minus 1, and then 2n minus 2, and so forth, until you get down to 3 and 2 and 1. 2n plus 3 factorial, you'll start with 2n plus 3 instead of 2n plus 1. But you'll still start subtracting 1 at a time. So subtract 1 from here, the 3 becomes a 2. Subtract again, that's 2n plus 1. Subtract again, that's 2n, that's just 2n, right? You subtract 1 from here, that's just your 2n. And that'll keep going until you get down to 3, 2, and 1. And you notice that starting from 2n plus 1 all the way down, that's the same as this 2n plus 1 all the way down. So those all divide away. A number divided into itself is the number 1. So here you still have a numerator. It's the number 1. Your denominator is 2n plus 3 times 2n plus 2, which we can now multiply. That gives us a numerator of 1. This is 2n times 2n, that's 4n squared. 2n times 2 is 4n, but then 2n times 3 is 6n. So 4n plus 6n will give us 10n. And finally, 3 times 2 will give us 6. Just like that. So if you take 2n plus 1 factorial and divide it by 2n plus 3 factorial, you end up with 1 over 4n squared plus 4n plus 6. That's our result. Okay. Lastly, for this section, let's talk about summation notation. There are occasions where our sequences are what we're after. We're concerned with, okay, what are the terms of this sequence? Or what are the patterns in the term of this sequence? However, just as often, there are times when we care not about the terms themselves, but the sum of the terms themselves. What is 3 plus 5 plus 13 plus 18 plus 23 and so forth? Now you might think, well, okay, but if it's an infinite series, if it's an infinite sequence and I add them all together, won't I get infinity? Well, maybe. Depends what the numbers are. If your numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, on and on and on like that, then yeah, they're going to keep growing and you're going to get an infinite amount. However, if your numbers are something like 1, 0, 0, 0, 0, 0, 0, 0, well, that's just going to add up to 1. Okay? So it depends on what your numbers are. Now, you might say, well, that's cheating. 1 plus 0, 0, 0, 0, that's cheating. We want to have actual numbers here. Well, there are going to be some situations where these are all non-zero numbers, but if you add them together, even if there's an infinite number of them, they still add up to some amount. We'll actually see a little bit of this later on in this chapter when we start talking about series, when we start adding together infinite numbers of terms. How do you add together an infinite number of terms? Well, that is a little complicated. So before we actually get to doing that, we want to first begin with the notation for adding terms. This is called summation notation. This is going to sound a little strange, but we're about to learn how to add. You say, well, we already know how to add. Well, okay, you know the basics of adding, but now let's take a look at some advanced adding. Yeah. So this is summation notation. One of the strangest things about math as you get into higher and higher levels is you start to realize how all the stuff that you knew how to do was just a little tiny bit of what's actually out there. Here, we're not actually going to investigate the concept of an infinite series just yet. An infinite series being what happens when you add together all the terms of an infinite sequence. We're not going to talk about how to do that just yet. Right now, we're going to talk about just the notation. How do you write that down? Once we have that covered in the coming sections, then we'll talk about how to do it. All right. So here we go. This symbol here is your plus sign. This is read as sigma. There are two versions of the letter sigma. This is the capital letter sigma, and then we don't use that for this class, but there's a lowercase sigma. So lowercase sigma and then capital sigma. That's the one we're going to be using here. This capital sigma, whenever you see it, you should think of it as a plus sign because it's telling you you're about to add some stuff. Okay, so what are you going to add? Well, we're going to add the terms of a sequence. So remember what a sequence looks. This tells you to add. Okay. Now remember, you have your a sub n's, and these are the terms of a sequence. And maybe your sequence is infinite, or maybe it's finite. It ends after a few terms. But here, regardless of whether it's finite or infinite, the terms of the sequence are denoted as a sub n. So here I'm not going to write finite or infinite because it covers both. Terms of a sequence. Okay. So the summation notation will basically look like this. You're going to have the sigma, and then you're going to have the a sub n. And these a sub n's will be whatever rule it takes for you to find your terms of your sequence. So you might have sigma of 5n minus 2. Or you might have sigma and then followed by negative 1 to the n over 2n minus 1. So here this won't always be a sub n. This will be the nth term of your sequence. So the rules for the nth term. Okay. Oh, but remember, your sequence goes on forever. So do I have to add them all together? Well, sometimes. Sometimes you're going to want to add all of them, starting from the first one all the way out to infinity. However, there are also finite sequences, so maybe you don't want to add them all together. Maybe you just want to find the first 2 or 10 or 50. You might just want to add the first 50 numbers of this sequence and then be done with it. So how do I know where to start and where to end? What do you mean start? Aren't you going to start with the first one? Not necessarily. For example, here's a sequence. Maybe I want to add starting from the third one up to the 50th one. I don't care about the first 2, and I don't care about anything after the number 50. So I need to know where to start adding and where to end. And if it doesn't end, I need to know that as well. So right here, around the sigma, you're going to have some notes that tell you where to start and where to end. Here, we're going to use the letter I. This letter I is not the imaginary number that you remember from college algebra. I stands for index. And this is going to be your indexing set. It's going to be the what? It's going to be the one that tells me where I start counting and where I finish counting. The way you're going to write it is you're going to say I equals, and then what term do you want to start counting from? Well, let's say I want to start counting from just the first term. Then I'm going to write I equals 1. However, if I wanted to start counting from the third term, I would write I equals 3. Or if I want to count from the 8th term forward, I would say I equals 8 or whatever. So here, this is always the letter I. We never use any other symbol. This number right here is often the number 1, but it will sometimes change. This tells you the position of the first number you will add. You say, okay, so here I'm going to start counting from the first one. Oh, but how far do I want to go? Do I want the first 5, the first 10, the first 50? Or let's say, for example, I wanted to add the first 20 together, starting from 1 all the way up to 20. Up here, I'm going to write the position of the last one that I want to add. Position of the last number you will add. It doesn't tell you what the number is, it tells you where it is. It tells you it's the first one in line, the 4th one in line, in this case the 20th one in line. It is the position of the last number you will add. So here, that little notation says a lot. It says, starting from the first one and up to the 20th one, you're going to add the terms that are given by this rule. This is summation notation. So let's see examples of this, yes? Let's go ahead and find sigma I equals 1 up to 5 of 3n minus 4. Okay. What this is saying is you have a sequence where the terms are going to be made up of the rule 3n minus 4. And what you want to do is you want to find the first one, and the second, and the third, and the fourth, all the way up to the 5th one. And once you find all 5 of those, you're going to add them together. They say a picture is worth 1,000 words. Well, it looks like, 8 symbols are worth at least a couple of sentences. So let's go and give this a try. This one will be, all right, the first number is what happens when you plug in 1. So 3 times 1 is 3, minus 4 is negative 1. The second number, 3 times 2 is 6. 6 minus 4 is 2. The third number, n is equal to 3. 3 times 3 is 9. 9 minus 4 will be 5. The fourth number, 3 times 4 is 12. 12 minus 4 is 8. And finally, the last number, I know I'm done because I've reached this number on top. 3 times 5 is 15. Minus 4 is 11. So these are the terms of this sequence that's given by these rules right here. And you're starting from the first number in the sequence up to the 5th number in the sequence. And then sigma says you're going to add all of those together. So that's what? 19. 19 plus 5 is 24. 24 plus 2 is 26. But then subtract 1 is 25. And there we go. The sum as n goes from 1 up to 5 of 3n minus 4 equals 25. And that's actually how this is read. Whenever you see the sigma with the index from 1 to 5 of this, the way this is read is the sum, that's what the sigma is telling you, it's a sum, you're adding things together. The sum from I equals 1 up to 5, or whatever these numbers are, from 7 up to 50, whatever the case might be, the sum from I equals 1 up to 5 of 3n minus 4. That's how you would read this aloud. The sum as I goes from 1 up to 5 of 3n minus 4. In this case is 25. Oh, actually, I made one little mistake here. Here we want these to match. So 3n minus 1, here I equals 1. Here I should have written this as an I. Because again, what this is saying is your I is 1, 2, 3, 4, 5. So if I'm going to use I right here, I should use I right there. If I'm going to use N right here, I should use N right there. If I'm going to use W right here, I should use W right there. You can use whatever symbol you like, but I and N are the two that we use just about every time we use this. Right? So yeah, that's just a little typo on my part here. These two should be the same because that is being replaced. This symbol is being replaced by these numbers, starting from 1 up to 5. There we go. So here I guess it should be 3i minus 4. There we go. All right, so go ahead and give this a try. I would ask you to find the sum as I goes from, let's say from 1 up to 5 of I squared. All right, go ahead and give that a try. Pause the video, give yourself the time you need, and once you have a result for this sum, go ahead and unpause and we'll go through it together. All right, so first of all, we're going to find, starting from I is equal to 1, we're going to plug that in right here. So 1 squared is 1. The next one would be 2. 2 squared is 4. The next one is 3. 3 squared is 9. The next one is 4. So 4 squared is 16. The next one is 5. 5 squared is 25. Notice we're just counting up, starting from I equals 1. 1 squared, 2 squared, 3 squared, 4 squared. Finally, we've gotten to 5 squared, and now we know that we can stop, because this is the last number that we're going to plug in. So now you're adding all those together. That's what sigma means. You're adding together all those numbers you just found. And what do we get? 25 plus 16. That's what? 30, 41. 41 plus 9. That's 50. 50 plus 4 is 54. Plus 1 is 55. Just like that. Okay. Going the other way is also sometimes very convenient. Sometimes you'll have a long summation, which is difficult to write out because it's so long. In that case, it may often be convenient to write it in sigma notation or summation notation. This book calls it summation notation. Other books call it, based off of this symbol, they'll call it sigma notation. You'll hear me use both. They're equivalent. They're interchangeable. If you say summation notation or if you say sigma notation, those are the same. Summation notation or sigma notation. All right. So let's consider, for example, let's say we're doing this one. So now we're going backwards. We're going to write the summation in summation notation. So let's try 6 plus 8 plus 10 plus 12 plus ... all the way till you get to 32. All right, so we're going to use sigma notation, summation notation. First of all, we know we need a sigma. That's going to be true of every time we use summation notation. So let's go and start with that. All right, we're going to need a rule that tells us how we can find each of these. Okay, well, let's see. They all seem to be, let's see, what pattern do they have? Well, it looks like they're 2 units away from each other, right? If you add 2 to 6, you get 8. If you add 2 to 8, you get 10. Add 2 to 10, you get 12. And that would keep going. You would do 14, 16, all the way till you get to 32. Okay, so it looks like you're going to take, you're going to keep adding 2's to that. Okay, but where do you start? Well, it looks like I start from 6. So I almost want to write this as, and here I'm going to use pencil so that I can erase and correct myself. I almost want to say 2i, because here that would be what? 2. If I plug in I is equal to 1, that would be 2. And then if I plug in 2, I get 4. If I plug in 3, I get 6. I get 2, 4, 6, 8, 10, 12. Oh, that's the right pattern. Oh, but it starts in the wrong place. Right? I don't want to start from 2. I want to start from 6. So I have a couple of options, actually. One option is I can just go over here and say, you know what? Let me start not from the first term of this. Let me start from the third term. So I can start with I equals to 3. That way, the first number I plug in is 3. 2 times 3 is 6. And then the next one will be 4. 2 times 4 is 8. The next one I would plug in is 5. 2 times 5 is 10. 6. 2 times 6 is 12, and so forth. So that'll work. My other option is, if I really want to start from 1, for whatever reason, let's say I really want to start from the number 1, well then that's too small, right? 2 times 1 is 2. Oh, but if I add 4 to that, that's 2 times 1 is 2, plus 4 is 6. The next one would be 2. 2 times 2 is 4, plus 4 more is 8. The next one would be 3. 2 times 3 is 6, plus 4 more is 10. So that works as well. So if ever you have the right pattern, 2i, but it's starting in the wrong place, you have 2 ways to edit that. One is you can modify this so that you can scoot it up, or the other way is to modify this so that you can say, you know what, I don't want to start from the first one. I don't want to start from 2 times 1. I want to start from 2 times 3, in which case you would have 2i and you would start from 3. And either of those is fine. Right? So I'm going to go ahead and, well, since I've already got this one written down, I think I'll use this one. But if you had I goes from 1 up to something of 2i plus 4, that would also be correct. So let me go ahead and just stick with this one. So I'm going to say 2i, starting from where I is equal to 3. You don't have to start at 1. And you're going to keep going until you get to, well, let's see. What number do I have to stop at so that the last digit is 32? Well, it's going to be 2 times some number is 32. Well, number's got to be 16. 2 times 16 will be 32. Oh, so I can stop up here at 16. And there we go. We take I goes from 3 up to 16 of 2i. Plug in the first one. 3 times 2 is 6. And you keep going until you get the last one. 2 times 16 is 32. And then you would add all of them together. So here this and this mean exactly the same thing. And that one is significantly more compact than having to write out all of those terms. Okay, so go ahead and give that a try. Write using summation notation or sigma notation if you prefer, whichever name you like. Let's do this one. This is 1 over 2 plus 2 over 3 plus 3 over 4 plus 4 over 5 plus ... until you get to 14 over 15. Go ahead and write that using sigma notation. Go ahead and pause the video, give yourself the time you need, and once you're done, unpause and we'll finish that together. All right, so let's take a look here. Notice your pattern. Your numerators are just the counting numbers. 1, 2, 3, 4, 5, 6, all the way to 14. Notice that your denominator is always 1 bigger than your numerator. So that's a 1, that's a 2. That's a 2, that's a 3. That's a 3, that's a 4. That's a 4, that's a 5, and so forth. So we're going to take a sigma, because that's how you know you're adding things together. Here, it looks like I want to start counting from the number 1, because I'm going 1, 2, 3, 4, 5. Okay, so I'm going to take I equals 1, and I'm going to stop counting when I get to the 14th term. First, second, third, fourth, all the way to the 14th one. Notice that my numerators are the same as whatever position I'm in. So my numerator should just be I. Because after all, if I is equal to 1, my numerator is 1. If I is equal to 2, my numerator is 2. When I is equal to 3, my numerator is 3, all the way up to 14. The denominator will be the same as the numerator. So it should also be I. Oh, but it's the same as the numerator, but then you have to add 1. Okay, so I plus 1. And there we go. This is sigma notation for that expression. And that's it. That's our answer. So that brings us to the end of this topic and the end of this section. If anybody has any questions, comments, or problems, anything you need answered, please go ahead and reach out. And I hope everyone has a nice day.